So today I'm starting with some advantage because already Choitalidi has given some idea or direction of the whole thing, and synchronizing with that idea, Surmilidi has given a clear-cut indication of what we want. So we are starting ACC A1 Mathematics and Statistics for Chemists. I would like to start with Tagore, Simar Majo Ashim. I dive down into the depth of the ocean of forms, hoping to gain the perfect pearl of the formless. The next comes from Galileo. The most mysterious novel in the universe is the universe itself, only written in the language of mathematics. And as you know, chemistry is no less mysterious and again written in the language of mathematics. And finally, from Leonardo da Vinci, no human inquiry can be a science unless it pursues its path through mathematical exposition and demonstration. So these are the three messages. The other name of mathematics, what we can call pearl of the formless or language of science or even path to the absolute truth. Whatever it is mathematics. And what does ACCA tells about that? It gives a message not to be a master of maths, have fun, enjoy and apply it. That is the message from ACCA 1. Quick webinars math. This is math course. We are given 45 minutes and that actually amounts to 2.5% only of the overall. 30 lectures of 60 minutes each and 45 minutes is given. So percentage 2.5%. Or even we just focus on a single unit, let's say the first unit, then that is equivalent to 16 topics are there and 8 lecture unit 1, 60 minutes each. So 45 minutes is equivalent to 1.5 topics. So if I go into the depth of maths today, it will take only 1.5 topic the whole time, right? So naturally I would not go in that line. Rather my line would be a bit pedagogical, not the depth of maths as such today. So I'd like to start with 3 interrogative signs. When you are in the class, that is when you are introducing some concept or idea fresh, what it is, and then why it is, and then what next. That means how you can apply that, right? So briefly, you can just touch these 3 interrogative signs, and then you start the outline and concept of the concept, and then as Choitalidi was indicating that less vigor and more understanding. And the next point is less derivation and more exercise. And then no less important, whenever we get the chance to be graphical or geometrical, then you please give the visualization effect to the students. And then most importantly, we have to connect the mathematics we are learning in the class to our physical science, chemistry, right, through known problems. They must not forget that they are in chemistry classes. Actually, they are not a dry mathematics class, right? Every time we make them remember, and more importantly, please try to teach these courses on your own, being chemistry or particularly physical chemistry teachers. Please don't leave it at the mercy of other departmental teachers, say from mathematics or economics or whatever, whoever the mathematics pundits are there in other departments. Please don't allow them or don't insist them to take these classes, but because of this physical science connection, right? And then you can give, of course you should give some references page wise if possible. And then one more important point, that's proportionate to number of lectures. That means the lectures assigned in the syllabus, you try to maintain your topic wise lectures according to that proportion of number of lectures. Suppose you like some topic X or Y and you are very expert really in that X and Y, and you took a lot of time for X and Y and just neglecting A, B, C, D. That should not be the case with students. This is a minor point. And provide study materials, if possible, make it a habit. So this is my starting point. And then deciphering the syllabus, a tough job actually. So if you fail to plan, then you are planning to fail. So let me have let me try to do some planning how I can introduce the subject to the students. First of all, if possible, then you make a day-wise distribution of the topics, right? 6 units are there in the whole syllabus, 6 units. And then next comes that for each unit, there are the subtopics for under each topic, and you have a distribution again proportionately. That means you are going for a proportionate content revelation, right? And then you are ready probably to go to the class with chalk and talk along with the power of the PowerPoint presentation. By the way, I will submit a separate PPT file to the organizers Kia plus Ajanta, and that is only for unit 1. The details that is in class chalk and talk etc. I will give for unit 1 only. Why only 1? Because it's a bit debatable, I think, that whether the teacher should be provided a ready-made handout or something material. Of course, students should be provided, but not the teachers. Some people say it's a kind of spoon-feeding thing. They don't prefer it. There is one thing, and why unit 1 then? That I'm coming later. Why unit 1 is so important out of the whole course. And so, well, in the last year, I had the opportunity to teach a few students on this course. So I am sharing my experience only, not very rich. Only 1 year I have taught. Okay, choice is of course yours. I would only share my experience only. Well, so let me start unit 1, topics day-wise distribution. And why it is unit 1 is so special to me, because unlike the other 5 units, all the other 5 units, they have a separate title, right? Say probability, determinant matrix, vectors, differential equation, etc. But unit 1 has no title. Why no title is there? Because actually it is a hodgepodge, khichuri. It contains so many of things, and they are not really so much related to one another, all the things. So that's why. Well, so out of that mixed up topics, I have classified into 3 categories, the whole 16 topics in 3 categories. The first one is you can call recap of basics. The second one is series expansion, and the third one is special functions. So 3, 3, 3, 2, 8 lectures, and then the topics goes like functions, limit, etc. in the recap and heading. Under series expansion, that is something new: Taylor, Maclaurin, Laplace, and Fourier. And special function category, there are 2 special functions we will learn: gamma function and error function. So the lecture distribution is like this, and a total of 8 as assigned in the syllabus. But I am 100% sure that within this short time, that is only 8 periods, it is just impossible to cover up all these serious things. So at least we need 12 lectures, and that I am calling it an unofficial distribution. Okay, 12 lectures. So that will get the PPT later on. Now I am going for the next phase of my discussion, that is proportionate content of the subtopics. A recap of basics, right? So we will start with functions. So we just keep limited the definition of what we mean by single valued, even or odd function, and to some extent hyperbolic and its inverse functions, right? And then limit and continuity. So we just focus on when does a limit exist after giving you the definition. And then continuity again starts with definition and the condition for continuity, and then you probably come into the physics or physical chemistry. Fix the fix. So you know the finite, integrable, continuous, and single valued, the quality of a good well-behaved function, and you have to fix that fix, and that continuity is there. So that is the relevance. And of course finding limits by Taylor and Maclaurin. Maclaurin and Taylor are in my syllabus, but I put a star here because it is not explicitly mentioned in the syllabus. So you may or may not go for this portion, finding limits using Taylor and Maclaurin series, or including L'Hopital's theory. And then derivative starts with geometrical interpretation, and then partial derivative. This is very worth doing, because partial derivatives, the whole lot is connected with thermodynamics, right? Euler's relations, Maxwell's relation, Joule-Thomson coefficient, everywhere the whole lot of partial derivatives are there. And then also this exact and inexact differential connection with thermodynamics. For example, you just give the basic definition of a perfect differential and total differential, and then you bring the practical problem of dV and PdV. dV is exact differential, and minus PdV is not exact differential, and that physical significance is that minus PdV is actually represents the work, which is not a state function. So that is the how you can connect with the physical problems with the something mathematical. And then comes the maximum, minima, and inflection point. Well, you just again give the condition of maximum and minima with some examples, and for inflection point better discuss the Van der Waals equation, which is in some other core course. So that's how you can connect the other courses with this maths course, right? And now comes the series expansion or transforms. Well, Taylor and Maclaurin. So Taylor series, just you can note that any arbitrary function, whatever complicated the function is, it can be expanded in a simple infinite polynomial series, right? Simple infinite polynomial series when you are expanding the function around x equal to a. But the CI, these CI actually are crucial. If you can find some way to find this CN or CI, then actually know the whole expansion. So how to find the CN? You can present it as a puzzle or play with some logic, and they can get it on their own. And if you extend this Taylor for a particular a value, say a equals to 0, then you get actually Maclaurin. So it is not so new. Taylor and Maclaurin are very connected, and you just give only 5 examples, 3 as examples and 2 as exercise. These 5 functions: sine, cos, e to the power x, ln 1 plus x, and ln x, right? And don't bother much about this other any examples. Well, this was in the form of an article. It is there already in the Bankim Chandra College and Physical Chemistry Teachers Forum volume 1, written by PD, myself. And now comes the next part of the first unit, Fourier series and transforms. So Fourier series, it is again expansion of an arbitrary function, but this time the functions are orthogonal, unlike the Taylor and Maclaurin. And well, for odd and even, you know, the cos will survive and the sine will survive respectively. Again, the coefficients are important, and there is some prescription of how to find a0 and an equal to 1 to infinity, and a also bm. So this is what Fourier series is. But what about Fourier transforms? This m and n are integer, right, in this expansion. But if you want, you can have m and n to be continuous. That means the summation sign over here, they would be replaced by integration, and it gives you a kind of broad narrow relationship, the Fourier transforms. So I don't bother much right now about these tedious expressions. It looks a bit odd, but fx and fk, these are two functions. One is of x, another is of k, and they are called the Fourier transform to each other, and vice versa, right? Where x and k are two conjugate variables, we call them conjugate variables. Another example of conjugate variable is energy and time, and as you know, the uncertainty principle is somehow connected to this Fourier transform, x and px, when k is px, and here time and energy. So that is actually relevant, very relevant to our spectroscopic part. As you know, that Fourier transform spectroscopy is very well known tool for spectroscopist, and that actually makes use of this Fourier transform between this broad narrow relationship between energy and time. In the same volume of PCTA Bankim Chandra College, Professor Kamal Bhattacharya has written an article on this Fourier series. Well, you can consult that. And then comes the Laplace transform, is again another transform, integral transform between two variables x and s, right? So fx and fs, f capital, f small, right? So these two are actually Laplace transform to each other. X and s are the two variables, or you can say in the other way that if you inverse it, that means L inverse f is given f. So f is the Laplace transform of f, and f is the inverse Laplace of f. So they are connected by some reverse relationship, and you just give a 1 or 2 example after giving the definition and then transformation and how you can use. So the outline of that Laplace transformation, many often we need solving a differential equation, right, and which becomes sometimes very tedious and problematic. Then what we suggest, that you just go for a Laplace transform to this differential equation, which is complicated one, and as a result you will get a simple algebraic equation. which is easier to solve. So you solve it and then you make an inverse Laplace transformation to get the original solution of the original given differential equation. So it's a kind of transformation forward and backward. We apply in mostly in a kinetic problem. So two problems are mentioned here. This is provided by Ankon. And another article by Professor Kamal Bhattacharya is again in the volume 1 on Laplace and transformation. Well, the third part, special functions defined as the integrals. Gamma function, well, you just give the definition and the recursion relation or gamma function. And as far as application, you may remember that in your kinetic theory of gas unit, we have used some standard integrals while evaluating the root mean square velocity or the average velocity. So where from we get all those standard integrals? Answer lies here. Actually, this is an application of gamma function, right? Error function, very close to this, again integral defined in terms of integrals. Again, you just give the definition. Of course, we computed by numerical integration that we are learning in some other course, and then the definition and evaluation at different points, error function representation, and more importantly, if you can, you show the graphical representations of the functions, that is a visual picture, and then you define the complementary error function. So just two functions, error function and complementary error functions. The definition, one illustration, and just two graphs, right? That's all. And then through graphs you can also explain the statistical interpretation and the applications. So that I have supplied in my detailed PPT in a separate file, all these things. Don't bother much right now, but rather I will take a few seconds or minutes on what I mentioned, that if you can make visualize, students visualize the whole thing. Ekti chobi hajar shabder kotha bole, so chobi is always important. First of all, for example, okay, when you are explaining derivatives, if you can give such a drawing and explain that it is not a division, dy by dx is not a division of dy by dx, it's rather mere a symbol, and how it comes, this graph helps you a lot to understand that. And similarly for integration, well, integration is actually the reverse operation of differentiation. So this person, this gentleman, is actually the result of differentiation of this Batman, and on the other end, this Batman is the integrated result of this gentleman. So they are inverse relation, and as well this area is nothing but the integration over a definite limit. So this is the geometric interpretation of integrals like the differentiation. And then you come to the error function. Well, error function, after the definition you put, you just evaluate these things from at least 3 values, because you need all these values for plotting. So the error function C, that means complementary error function, you see 2, 1, 0 at minus infinity 0 and plus infinity. So you give some minus infinity, it's 2, and then it is it is 1 at 0, and again at plus infinity it is again at 1. So 2, 1, 0. And you can draw both error function and complex complementary error function in a single graph, and looks like a very symmetrical shanashi. You can explain this, so they can easily remember if you show them the plots, right? And that can be very much part of our exam as well. Well, another examples of okay, error function that I was explaining, error function. So this is very known to all of us, a Gaussian distribution. A random variable when distributed, it follows the Gaussian distribution, probability distribution. And if you want to find the probability of between say minus x to plus x, so what we will do? Integration, right? The area under this curve would be given by the integral of what function, of this function, that is Gaussian function, over the limit of what? Minus x to plus x, that is the given range you want. And this is nothing but the error function, right? And the remaining part, that means this white portion, the right and on your left, if you again are interested in finding the area of these two regions, then again you have to do the integration over a different limit, and this is exactly the complementary error function. So that is the meaning of geometrical significance of these two functions. A YouTube video is there which attempts to also explain all these things through Excel, use of Excel. So for visualization aspect, and it was done by PD, myself. You may consult. Another example is a similar font that I was talking about, that the number of molecules, what is the probability of the molecules, fraction of molecules which may have velocity or speed range from minus to plus something u0 say. So again it's an integration, and this can be taken as a standard problem, and here we see that we use actually some error function. So that is how error function can be used in chemical or physical application. This is another example of quantum tunneling. Well, I'm not going to discuss, it is there in the detail PPT. Now a few minutes I will take more only on proportionate content of the subtopic. So I have finished unit 1, which was basically focused on because for that unit I am giving the in-depth separate study material, a separate PPT, but for the coming units, unit 2, 3 and 4, I will not be giving any such detailed study materials. Rather I will give only the proportionate content of the subtopics.